Hi, I'm Dr. M. Kamakshaya, open source software evangelist, and I'm also a full stack web developer. For the past few videos, I've been explaining how to write R programs for data analytics. I'm explaining how to perform the data analysis using R programming language. In my previous video, just before this video, I explained control flow, and I gave a very brief demonstration on different types of conditional statements like if else, nested if, and also vectorized if, but I didn't explain switch statement, and there is another couple of methods to perform check the conditions and perform the logic. I also explained loops using for and while, but I didn't explain another special method called repeat. So they are not much important. The switch statement and repeat, I request you to study yourself. You have a lot of information online as how to use these statements. So I humbly suggest you to just use and go through. Okay. Now let's go back. So this was where exactly I stopped. In this video, I'm just going to explain you how to perform the correlation. So what is correlation? How can we understand correlation? So now I again advise you to go to, suppose if you don't know what is correlation, then just straight away go to Wikipedia and study correlation coefficient. Usually whenever we talk about the correlation, it is just simply refers to, most of the times it is called Pearson correlation coefficient, or small r. We just simply call it small r. So you need to study what is correlation coefficient, and then there is a probability space for this coefficient. The minimum value for the correlation coefficient is -1, and maximum value is +1. This is called probability space. The value change between these two limits. And then you got, I think this did not have, this is not the exact page. I think you should be having a link here somewhere called Pearson, product movement correlation coefficient. Now here Pearson correlation coefficient. This is also called as called Pearson product movement correlation coefficient. So it's just a small r, that's all. Examples here, visuals. This is what is the expression. Whenever you are trying, the aim of the correlation is to find the association. There are different types of correlation techniques. You need minimum 2 variables. Actually, correlation falls under a particular category of analysis called bivariate analysis. You need minimum 2 variables to perform the correlation, because there is no meaning for the word association in absence of for one single variable. It is not possible for us to find the association between a same variable, right? So we need 2 different variables to perform the correlation. Now the mathematical expression for the correlation is the ratio of covariance to that of the covariance over the product of the standard deviations of the variables. Here you see x is a variable, y is a variable. First you need to find the covariance, and then you need to, the correlation can be obtained by dividing the covariance between the variables with the help of product of the standard deviations. Now that is not very much. This is actually the sample correlation. Covariance is xi minus x bar multiplied yi minus y. The xi and y are the values of, xi is the value of a variable x, yi is the value of the variable y. Now each value is, the mean is subtracted from each value of x, and that amount is that value is multiplied with the same value of y. And now these are the standard deviations. You see here xi minus x bar whole square, square root of y minus y bar whole square. This is standard deviation for y, this is standard deviation for x. And at top of the ratio in numerator we have the covariance, and this is another way of finding the. Now I am searching for a particular measure, that is this is cos theta. This is in mathematics we try to figure out the association with the help of length of a vector, and the covariance is dot product, and that is divided by the product of the length of the vectors. Anyway, that is a different thing. And this is what I am searching for. Whenever you perform correlation, you also need to perform correlation significance test. This simply means that there is a hypothesis in correlation analysis. Whenever we perform the correlation, it is just a sample information. So when the correlation is computed, the researcher or the statistician also have to prove that the same effect is also available, may be present in the population. So that is what is called the hypothesis testing. Now in sample we refer the correlation coefficient with small r, and in population it is referred as rho. You see here, in population the correlation coefficient is referred with the help of rho, and in sample the correlation effect is referred with the help of small r. Now this is a significance test for the population. What we are trying to do here is that we are converting the small r, which means Pearson correlation coefficient, into the corresponding t value. And anyway, in a programming language like R, computing a p value for t value is not a big thing, and so whenever a t value is calculated based on r value, that t value will be converted into the p value, and based on that p value the decision is taken. So this is how things, and we can also reverse the t value into r, the corresponding r value. That is very useful. We can also convert we in the sense the r value is also can also be converted into f value, z value, chi-square value, many things. You can do a lot of gimmicks, the magic around the Pearson coefficient R. Okay, the theory apart, and let us swing into the action. And now I am going to talk about performing Pearson correlation coefficient, and you can also perform a couple of other correlation measures. What are they? Now suppose if you want to know the, as usual, whenever I'm telling you how to pick up the syntax for each and every statistical procedure. Suppose if you don't know how to perform correlation, there is a function called call, help call. Now you'll get very minimum documentation for correlation. Now you can just pick up the syntax here. This is variance, covariance, and correlation. All of them covariance to correlation, something like that. So here there are examples, bottom of the documentation. You can just read all of them. And now please be cautious. The hypothesis, null hypothesis, is going to be like this: rho is equal to 0, which means though you have some certain, after we calculate the Pearson correlation coefficient, we come back and check, we perform the correlation significance test, and with the help of the p value we need to take decision whether we are whether the null hypothesis can be rejected or accepted, something like that. That is what is called the hypothesis testing in correlation analysis. Okay, now we need data, and then I'm just going to introduce you some data. That is, you can take any data, but the base for the criteria for the data should be common. That is what I would like to tell you. Now I have some stock market data. Let me show you some monthly prices of HDFC. I downloaded some data, that is monthly prices of HDFC. These are the stock prices of HDFC Bank, and I am going to compare this data with the same that of Axis Bank. So I have the stock performance prices data. I mean, stock returns or prices or prices. Stock prices data of two different banks, HDFC and Axis. I am performing correlation to compare these two and find the association between them. That may be foolish. I mean, that may not be a good example for correlation. But maybe I think in research and academics we have the habit of, for HDFC never want to, I don't know if they are interested to compare their prices with Axis. They can just, even for that matter, they can compare their stock prices with, people do these comparisons. Suppose if I am investing in HDFC and I already invested in Axis, and if the Axis is performing well, then I compare HDFC with, if I am happy with Axis, why can't I compare with HDFC? So that can be kind of, and in stock prices analysis, in stock market analysis, correlation is one of the sought after techniques. The stock experts always employ multivariate correlation to compare the stock prices, and they have their own observations. I just don't want to here come back. Somehow I already have that data in my session. Let me show you LS. I have this HDFC, I have Axis, and I'm going to make comparisons between these two data. Now let me show you Axis. I have this data. Let me push this little upward. Now you see BIM, Axis. Sorry. We have 12 rows and 7 columns, and then HDFC, BIM, HDFC. We have 12 rows and 7 columns. So this is what I was talking. Then both of them should have some commonality. So you cannot have two different data sets with different dimensions. You have to check all these things. And one more thing, that these dates, there must be one common parameter. You must have a common point to compare these two data sets, either by some criteria. Like here we have the date. We can compare. Date is a common variable in these two data sets. Then only it is possible for you to perform the correlation. Actually, many times in industry and in academics, correlation is done just like that, willy-nilly, the requirements of correlation. That is not correct. You need to have some commonality in both of the data sets. Then only the idea of association arises. Otherwise, there is no meaning. Now, how do we need to perform correlation? We cannot just simply go HDFC and Axis. So that is, or is not going to listen to you. There is a way to perform this. Let me explain you the bivariate correlation first. So let us take the close prices as usually. Most of the time people are interested in close prices, like date, open, high, low, open, high, low, close, okay. Anyway, volume is not going to. Yeah, you can also. Volume is, I think, most interesting. Should be most. Apt variable to bring comparison between these two banks. That's most. Okay, we'll do on volume and then we'll go back to close price. Okay, because volume refers to the total value of the firm. Now core, I am just going to bring indexing into action. HDFC, then I am going to index this. Now I see 1, 2, 3, 4, 5, 6, 7. Now the seventh one is the volume. Now Axis, same, seventh one is the volume. Now let's, oh my god, there is 96% of, I cannot say percent. This is a Pearson correlation coefficient. The association is very strong because the value is 9.9. It is close to 1, right? As I have told you, the probability space for the Pearson correlation coefficient range between 0, 1, 2 plus 1. You see, this value is very close to plus 1, which means very strong association between. So if someone is already invested in Axis and they are happy, so they can surely, they have to invest in HDFC is one of the good options for them. something like that. Now this is just in terms of the volume, so we really don't know how the stock is performing, so that we can only judge based on close prices. Now the close is going to 1 2 3 4 5, fifth variable. You just have to change this fifth one, okay, index. Now we'll see, oh my god, actually the stocks are also close, very close, they have similar performance. You see, this is the monthly data from 2019 5th month to 2024 till April. Very latest data sets. 94% of association between, in terms of the close price. You can also perform that in terms of the open price, and the open price, the association between open prices of these two banks, 89%. Okay, so opening, they have, you see, actually this is not a percentage, don't misunderstand. The association is not that strong compared to the close price. Close price has very much association, very strong and positive. Any value above points, by the way, you have a criteria, you can just usually any value above 0.5 close to 0.9 is criteria to interpret. You have every damn thing online, okay? Interpret correlation value. So this is you see here +7 is very strong, 0.5 moderate, 0.3 weak kind of thing. I don't need to open this link, this is sufficient for us to. So anything above 0.5 is okay, more than moderate effect kind of thing. Now this is how the bivariate correlation is calculated. Since this is continuous in data, these are all ratio data, so I perform the Pearson correlation coefficient. Now you see, for correlation there are different types of methods. You see, when you are performing correlation, by default it performs the Pearson. Suppose if you want to go for the Spearman, this is for rank correlation, Spearman row. It is referred to Spearman row. It's called rank correlation. You have rank data just like ordinal data, then you have to perform the Spearman. I am not doing this because I don't want to make my demonstration lengthy. In one of my demonstrations I was talking about behavioral data, where we had some satisfaction kind of activity. There you can compare, you can perform the correlation in between the same factor. Like if you have three different variables for which explain satisfaction, you can perform multivariate correlation for all those three variables, something like that. If that data is ordinal, then you need to choose this. You have to mention method C, Spearman, something like that. If you have nominal data, then you have to go for the Kendall-Stowe. That's the best option. So Spearman is a big brother, is a generic method. You can just make use of, you can use this method. Spearman is used for in all the circumstances, but Kendall is used, the method Kendall is used only if the data is nominal. The Spearman is used if the data in hand is rank data or ordinal data, something like that. So this is bivariate analysis. Where are we going to use this control flow? I'm just going very close to that. Now suppose if I would like to do some multivariate correlation, like say this information is not sufficient for me, I want to check all the variables, okay, then I need to do this. I'm just going to use same indexing 227, right? Yeah, and then 227. You see, perform the correlation from second variable till seventh variable, something like this. Now you see you got all correlation, small r coefficient, correlation coefficient r. This is between open and open, which is ridiculous. Okay, now this is between open and high, open and low, open and close. You see, the open and close has just above moderate association, and then you have the volume. Anyway, this comparison is open and close is a fair comparison. Open and low is also, you can compare high with low. You see here 69% of association. Close. By the way, I'm not explaining you the. I mean, this is how stock market prices are saved or available to the researchers. These prices are saved in 7 different ways: open, high, low, close, adjacent close, something like adjusted close, something like this. And this is actually the worldwide commonly accepted format to retrieve, save, or process stock market prices. You need to know what is open, high, and low, close, something like that. Open is something can be compared with close, high can be compared with low, something like that. So you need to pick up the values, which is what is the open versus close. This is the, suppose this is HDFC, right? HDFC is organized in rows, and axes are organized in columns. Now the open price of HDFC can be compared with, I'm extremely sorry, I was interpreting in a wrong way. So the open price of HDFC is very strong and positive when compared with the open prices of Axis, and high prices of HDFC also strong and positive. Are there any negative? Yes, here there is a negative value. Volume and adjusted close prices are negative. Anyway, that is not a good comparison. You are not going to. You see, volume is volume of Axis is 96.85. This is actually the value which we calculated. See here, 96.85 the volume. Like this, this is what is called multivariate correlation analysis. Now we need to, whenever we perform the correlation, we need to perform correlation test. Okay, Pearson correlation test. Now how are we going to do that? There is a function in R called core test. This is actually the hypothesis, this test hypothesis, that the null hypothesis is rho. Though we have some certain sample information here, but this information, whether it is true or not in population, need to be checked with the help of a test. Now I already have that in history. Let me go back to, let me perform Karl Pearson correlation coefficient test. Okay, let me call it correlation test. That's very simple. Let me not, I don't know why I'm making things too complex for. Now this will return you a p-value. Here you see same t-value. I was talking about this t and p earlier when I explained you you need to pick up this p-value. You see this p-value is very close to 0, which means we can reject the null hypothesis, and we have very strong evidence in support of the alternative hypothesis. Now what is the null hypothesis? That is what is, see here, the null hypothesis rho is equal to 0, which means though we have some certain effect here, this was the coefficient, the effect in the sample, this may not be true in the population. So we've taken very small sample from some centuries of information, and not a century, actually some years of information. We just took a very few months of information, and in that sample we found this value, but this value is true in population. Taken all the information, data of this historical prices, can we find the same effect in the population? No. That is what the test is saying. You see here the value is far below threshold value, which is 0.05. At 5% significance level, we can easily reject the null hypothesis in favor of the alternative hypothesis that the rho is not equal to 0. The rho is not equal to 0, which means in population we have some certain effect. So it is, see, I think I am confusing you. So this is actually called association between these two variables. Volume of HDFC and volume of Axis. They are very strongly correlated. Now the hypothesis, null hypothesis, is that, so we have very strong and positive correlation, but the judge statement. The judge says that though you have some certain positive and very strong, but I don't believe in this. I assume that the actual correlation value could be 0 in population. Then we have to perform the test and then provide the evidence. This is evidence that the judge statement is not true, which means we have very strong evidence in support of the alternative hypothesis that the rho value is not equal to 0. So whatever the effect that we are perceiving in the sample may be true in population. So this is how we, so in population, from the student level, you just have to say the null hypothesis is rejected because the p-value is close to 0. Null hypothesis is rejected, and alternative hypothesis, we have evidence in support of the alternative hypothesis. Your job ends there. But as far as the decision is concerned, yes, in population the effect is also, the association is also positive and probably strong. So that is what is the inference or decision. This is bivariate called the coefficient test. Now how to perform the multivariate test? So because you don't have, now we need a loop, the control flow to take care of this. Now what we need to do, you can just use the, so for example, if you use I'm sure you will bog down. Yeah, error. So it is not possible for us to do this just like core. We need to figure a way. Now I'm just going to make use of nested loops. So that is just like nested if condition. Here I explained to you nested if condition in my previous video demonstrations. I'm just going to use nested loop. So what I did here is this. We need to do this in two different, so we have the multivariate correlation here, okay, correlation coefficients, but we need to figure out the p-values. So is this true? Like, there is some certain association between open price of HDFC and open price of Axis, but is it true in the population? This is only a sample statistic, but can we find the same type of effect in the population? So if that is then we need to find out the p-values for each of this call Pearson coefficient R. Now for that we need to perform that into two different steps. Here we have a matrix of 7 by 7. See, 1, 2, 3, 4, 5, 6, 6. No, 7, 6 by 6, which means 36 elements in this matrix. This is actually a correlation matrix. In statistics, we refer this to correlation matrix. What is the order of the matrix? 6 by 6. The total number of elements is equal to 36. Now we need to make a dummy matrix of the order 6 by 6. And this is going to be just a matrix with dummy value, a missing value. Okay, not available or anything. I just call it as NA. This is one of the data types in R. Now we need to create a matrix, a dummy matrix with 6 by 6 order, and then I'm just going to use a for loop. For I in 2 means we are starting from the first variable is date. Please be cautious. The open is second variable. You see here names HDFC. You see the first one is date, second one is open. So for I into 2 dim second value, second dimension, dim of HDFC. You see the 7. So 2 to 7. So 1, 2, 3, 4, 5, 6. So totally 6 variables. You see here 6 we have. So from 2 to 7, this will yield you 2. Let me show you that. Second, the 7. That command will return. What is the return value for this command? It should be 7. Dim HDFC 2, which is 7. Suppose if I use 1, that is going to be 12. This is the first value, this is the second value. We need second value. Now I in, you can just use 7 here. You mean 2 to 7 can be okay, but suppose if you have some n number of values, so this is actually the perfect logic, and if you want to make it imperfect, then you can just use 2 to 7, something like that. So 2 to 7, this is the 7, then inside the, one more loop, and this loop is for axis. For j in, this is I, this is j, please be cautious. J in 2 to 7, same 7. So now compute the correlation for I versus j, HDFC I, HDFC j. For each I, when I is 2, entire j will be finished for this statement. So now R computes correlation test and return this p-value for each of I and j. So that is what is the meaning of this nested loop. Now what I do, I just try to show you this. Maybe I am, say suppose I just remove this here. I just simply print. Okay, now not even this I comma j. Let's see what's going to happen. See, you see you got all these values. I'm sorry, I comma j. There is only whenever I use this comma, it is not accepted. Okay, see I comma j, that is correct. Okay, now come on. Okay, one more bracket, parenthesis. Say, now let's see what's going to happen. I even delete this. I just simply put it as 7. Now from 2 to 7, for I in 2 to 7, for j in 2 to 7, print I, just ij, and let's see what's going to happen. Now you see the I, for I, when I is 2, for all I till here, I 2, 2, 2, 2, 2, 2, 2, j changes. For when I is 2, j is 2. Then when I is 2, j is 3. When I is 2, j is 4. You see, I is same till 7 iterations. There are 6 actually. 1, 2, 3, 4, 5, 6, 6. For 6 2's, the value of j changes. Now this is what is the indexing of. Now what we are trying to do here, we are trying to compute the correlation test and take that p-value and put it in this matrix. That's all. We have the same 6 by 6 length matrix. Each element of this matrix is going to be the p-value from this correlation test. That is what simply we are trying to do. Okay, now let us execute the CD, dummy matrix, and now let us use this nested if to compute. Something went wrong here. Ij p-value as it is as I'll come back. Actually, I was trying to do the mistake here. That is, I was trying to define this as a unique. We can't do this. Okay, we can do this, but the problem is when we are using I comma j, this is turning into 2 2. The first value is going to be 2, so it is going to start from 2 and ends with 7. Whereas so here in that case, what is going to happen? We need to give 30. We can't afford to give. You see, the conflict is arising between the index, the size of the matrix, and the way we define the index here. You see here we have 36. Either you can have 36 or 6 by 6. Doesn't matter. You can also define 6 by 6. But when we define this matrix, when this matrix is defined as 6 by 6 order matrix, you see here it is going to start from 2 comma. See, when the I value is 2, j value is 2. You see, this is the index is going to be 2 comma 2. Whereas this matrix, the first element starts from 1 comma 1. That is what is the problem. By the time it reaches to the end, which means 7 comma 7, it is going to have 49 elements. That is what is the problem. So, but whereas here we have only 36. Now there is an error that the subscript is out of bounds, which means we have only 36 elements in this matrix. Order is 36, 6 by 6, but whereas we are producing 7 by 7, 49 elements. So that we have to take it off. Now what happens, either you have to change here 7 by 7, you can keep it 7 by 7 and then come now this time you just see what's going to happen. See, now R is silent, which means it has done something. Now go back and execute. You got the matrix. These are all p values. Now anyway, you got the first row, that we can get rid of. That is not a big thing. I can just I can also show you that minus 1 CD is CT is CD minus 1 comma minus 1, and then it's not going to be minus 1. First row, and then CD is CD minus 1. That is going to be the first column. Okay, sorry. So that is why I don't want to talk all these things, because there will be a lot of confusion. You see, now we got rid of, I think we still have that did we, okay, now, okay, let me not talk about this again. I will be wasting a lot of time. Now I'm going to see, the logic is like this. I'm going to create a matrix with 7 by 7 order, which means this matrix has 49 elements, and now I'm using nested loop, which means the loop inside the loop, and the iterator, I for the first loop is going to be 2 to 7. This is the dimension dim's second value, which is 7, and the iterator for the second loop, inner loop, is 2 to 7. This value, this is going to create the, why I use this dim function, because here in this situation we have only 7 variables, but in reality you may be having 100 variables. No, that's not going to happen. But this is the perfect logic. Let us write things. There is always a way that we end up imperfectly. There is a different thing. There will be a tinge of imperfection in our analysis. Now inside this, what I am going to do, I am performing the correlation test, and that p value I am going to save here in this index. In this address, in the address I comma j of the matrix CD. So this is actually, so let me finally once again do this. Now you see, let's come back here, and you see we got these are the p values. You see the p value for, let me do that. Okay, let me not give up the row 1 minus row 1. Now let me go for CD now. CD. Okay, the first row is we are done with the first row. CD. Now let's see what is the CD. Yeah, now CD is CD minus column, first column. Now let's see what is CD now. Yeah, we got a perfect p-value matrix. Now let us go for the correlation matrix. I think I have in history. Where do I have that correlation matrix? Should be having that correlation matrix in there. Yes, here, correlation 2 to. This is the command. Let me press this. We got 2 to 7. This is correlation matrix, and this is correlation, p values for this, each of this correlation coefficient. Now for this is the value for the correlation value for the HDFC open versus axis open. There is very strong and positive correlation. Now let us look at this p value. When the p value is 0, which means we are rejecting the null hypothesis that the rho is equal to 0. So what is the value that we are finding here? That seems to be that seems to be free from the error. This is not there is no sampling error in this value, and this value appears to be a genuine value. That is what we would like to convey. So in the same fashion, shall we pick up any value which is beyond you see here it is not close to 0. Yeah, here you see here, yeah, this relationship is a bit dubious. This is yeah, p-value, and the this is negative value. That is why it turned to be. You see here, yeah, this is a meaningless relationship. Like the association between the HDFC volume versus high price is negative. That is anyway uncomparable. We cannot compare these two variables. We can forget this. And anyway, so how do you interpret? Suppose if this is a meaningful relationship, now the value is negative, but it is very poor, weak, but the p-value is very strong, which means we can't reject the null hypothesis that the rho is equal to 0. So you see this is close to 0, and the p-value also says that the value in population is close to 0. So that way also there is no sampling error. The sample is speaking exactly the way. I mean, this is a perfect sample of the population. That is how we can conclude. Is there any other value we can find anything greater than 0.05? No, we don't have any value. So this is the only value which is beyond the 0.05, close to 1. There is a meaningless relationship. But most of the values that whatever we find here in this correlation matrix, there seems to be free from the error. They are not erroric values. They are all genuine values. So we reject the null hypothesis in favor of the alternative hypothesis. That's how we can conclude. That is enough for this video. I think I don't want to talk more and more. I don't like to add further. I just have explained you how to find the correlation coefficients together with p-values, and there is a very simple way we can just automate this entire activity by writing a function. But anyway, that is too much. This is too much for this video till now, and I may possibly explain you how to do that in one of my next later videos. Okay, thanks for watching this video. Please press like button and stay tuned for the new content. Kindly subscribe to my video channel.